So, hello everyone, good morning. My name is Filip Rezabek and I'm a PhD student at the Technical University of Munich. I'm very happy to be here today in the TUM Blockchain Club conference, and it's a great pleasure to present to you motivated students and also in general industry leaders that are passionate about new technology, want to learn. And for that, we will be talking about history, evaluation of blockchain, how it basically got us to the place where we are now. And it's especially quite interesting to talk about history because the topic itself is rather young, but already there is so many changes and so much innovation going on, which I think is also the part that made me interested in the topic, because you can see each year huge milestones and huge improvements are being achieved. And I'm really looking forward to what the future in this direction can bring. So, few additional words about what we as a chair of network architectures and network services are doing. So with starting with the topics that are relevant for us as the audience, so in case you're in general interested in this type of topics, feel free to reach out anytime in the future as well. But starting with the first one, of course, obvious distributed ledger technologies and blockchain, definitely something that we are very much passionate about. Second part that I think is going into more advanced cases is focused on confidential computing and usage of trusted execution environments in the environment of blockchains. Second part that kind of goes hand in hand with the distributed systems is also certain decentralized cryptographic primitives, for example, like threshold cryptography, that is being used quite heavily in, for example, custodial wallets, protection mechanisms, but also, of course, on the side of non-custodial solutions. So this is definitely quite an interesting technology, and other aspects like smart contracts, post-quantum cryptography, and so on are basically our daily activities we are looking into, not only from myself. For me, the main three topics are on top, but in general, as a small research team that we are, out of 25 researchers at the chair. So in general, the chair focus is focused on expertise in protocol design, security assessments, and so on. So in case you are TUM students or in general interested in blockchain, feel free to reach out. We are always looking for discussions with like-minded people. So starting with the talk itself, firstly, I want to briefly mention, of course, what is a blockchain. I believe most of you know it. Who knows it? Maybe just quickly, hands up. Perfect. So we have highly educated group of audience, which is good. So that way, hopefully, my talk that will be more in the lecture style will not be too boring. And if you have any questions during the run of the talk, feel free to raise your hand, and hopefully someone will bring you a microphone, and we can also have it more interactive, so that way it's not only me talking. Afterwards, we will dive into the historic overview. Again, historic in quotes, because at the end, the technology itself is rather new, but we will see actually it's building on top of a massive historical piece of research out there, and to try to also answer why are there actually so many blockchains and what the future holds for us in this direction. So first, just a plain definition. What is a blockchain? So in general, you can think of it like a coordination among many parties. So it can be, for example, all of us, like we are in the audience, when there is no single trusted party in the system. So of course, this, as you can see, is providing quite a strong constraints on the system itself, where no single trusted party is in the system. So if your solution can actually rely on a trusted party, you have to question yourself, do you actually need a blockchain to build it upon? But in general, trust is also a spectrum, right? You don't have like really trusted and untrusted, but there is also different levels of trust. So if you see, actually, it might be I trust that party, but I want to, for example, have certain properties like traceability, accountability, and so on, maybe still actually blockchain solutions can be very much relevant for you. Diving into the more aspects of blockchain itself, so you can think of it like a data structure that basically is grouping various data. By data, in our context, we are mostly talking about transactions, right? Because this is the information that we are exchanging between Alice and Bob in the system, and we are grouping them into blocks. And the blocks that are later on part of the blockchain, right, are chained together in a order-preserving manner, and more importantly, they only work in an append-only manner. What does it mean? That once you store something on blockchain, basically you can only append to it. You can't really easily erase the corresponding block, because when we are calculating the history from the beginning of the block until the end, we are going through the block one by one until we reach the current status. So it means that if someone would take a block number 3 at the beginning away, the history couldn't be like really easily computed. So this is the part that is really important to keep in mind. It's append only manner. And next very important aspect is that each of us in the system have to have the same view of the system within a certain period of time, which basically means that we are spreading this information about the latest block, broadcasting it to all of the peers in the system. So this is very, very important concept in this case, because if we don't have the same view of the system, the same state, it basically can result in certain type of conflicts, or we have to basically get up to date with the chain. So this is something to keep in mind, because always the chain is evolving. When we want to interact with it, we have to basically always get the latest information. And how this information and the state is being maintained, it's ensured by consensus protocol that is basically trying to offer security against various types of attacks. So basically, eventually you have various blockchain nodes in the system that are having the copy of the same ledger that is part of the system itself. I already briefly touched on that, but basically a very crucial aspect in the performance, but also, as we will see next time, but also a very crucial aspect in the preserving of this order in the system is consensus mechanism, where it is a responsibility to decide about the next steps in the system. So when we have a block, we of course have to agree on which block will be added to the system next and next and next. So basically you can think of it from the genesis block, that is like the first block that is minted. We are adding individual blocks until we basically reach the latest stage, and the blockchain keeps building on top of that. And there are various ways on how and who can decide to actually be the block proposer, which is also part that we will see on how the innovation in blockchain came and how it basically allow for large-scale deployments of such solutions. When it comes to a bit more formalized properties of consensus mechanisms, we are interested in persistence, meaning that the data can never be removed, which is the aspect of append only, right, of the blockchain as well. Safety, meaning all honest participants have the same data, meaning that if someone would have a different information about the ledger, of course it's a problem, because then they will be working with different information and they wouldn't be able to interact with the system. And lastly, liveness. So if you have honest participants in the system, where every system has a certain assumptions on how many honest parties there are in the system, either it's 50%, 2/3, and so on, it's always important, especially the honest parties that want to interact with the system, actually are given the opportunity to actually do so. And the last one in brackets, because you can, of course, have blockchains in various deployments. For us, and I think for the conference, we are mostly focusing on the permissionless scenario, that anyone that is out there can actually add the data. Sometimes you have to pay a small fee. Depending on the chain, the fee can be a bit larger, but in general, everyone should be able to add the data and interact with the system. So with that out of the way, we roughly set up the basic understanding on what blockchain is and how it proceeds, which I think for you, maybe already you know it, just wanted to provide a bit of context. And with that, we can dive into the aspect actually of the history and evolution of blockchains itself. So this is a rough timeline. So as you can see, the first generation basically started with Bitcoin in 2009, which is actually not so many years ago. But since then, we can see that there is quite an active evolution and many new generations of blockchain have been released. Nevertheless, what we shouldn't forget, there is a long body of research coming from the traditional Byzantine fault-tolerant systems, consensus mechanisms, that later on was possibly applied to also some of the more recent systems. And we basically could improve and build on top of that, because as it is always in academia, we are trying to build on the shoulders of giants, right? And with that aspect, basically, we can use some of the expertise that is out there. So that way, I think it's also a very crucial aspect when it comes into consideration when people are saying that technology is not proven and so on. You have to also take into mind that there was actually a lot of body of research done before. That means that we are not starting something completely new. We are just innovating on top of some previous information as well. And looking at the first generation, we already covered. The second generation, we will dive into more detail later on. And especially the third generation is the part where we are now, where also we later on started to see more aspects of specialized blockchains out there that are focused on particular use cases. And with that, we also see a plethora of various types of blockchain protocols that are working. And now, in 2023, the next big part, the next breakthrough should be aiming for the mass adoption, right? So from that, I will also provide some perspective from the other way, rather like How far are we from the mass adoption? This is something that I cannot really answer, but we'll try to rather look at it from the perspective of the technological status and try to bring maybe some discussion points on how far are we actually from mass adoption from that point of view. So starting briefly with BFT, traditional BFT especially, as you can see, the initial terms were coined in 1982, so it's been already quite a couple of years. So I think for that particular case, we can definitely talk about some history that is a bit extended. And the main aspect that I think I want you to take away from this slide is that the traditional BFT focused on a set of predefined nodes. What does it mean? When we are starting the system, we know how many parties will be in the system, and it's much more static, so we don't usually change the system and the number of participants. It usually stays that way, and we design our system to be working in such a way, and it's a bit tricky if we want to make parties away. It's definitely possible, but they should be within the certain bounds that we design our system for. And of course, each of the parties in the system are communicating with each other. This stays the same for also current blockchains. And there has to be some information about how do we actually ensure that in case the nodes misbehave, we are aware of that. And for that, we are talking about the Byzantine fault tolerance, where we actually want to ensure that even if they are misbehaving parties, they lose communication, or actually they are actively trying to crash their nodes and their operating system, whatever stuff, the system actually should be still able to ensure the persistency, liveness, and safety. So an implementation of such solutions, for example, PBFT, I don't have time to go into the details of that, but general takeaways, it's very fast for a small number of nodes, which is basically the state of the art of traditional BFTs before Bitcoin was introduced. There was, of course, some new breakthroughs since then, but I would say still the general idea still holds. And aspect that I want you to also consider is determinism. What do I mean by determinism? So once you go through the communication among the peers, you basically reach consensus at the end of the individual communication rounds, which is quite different, as we will see when it comes to other type of solutions out there. But overall, we will come back to it several more times in the upcoming slides. What, of course, is the aspect that we have to consider? I was talking about the advantages, right? It's fast, it's deterministic, and so on. But we have to also consider why, when there was so much resurgence in traditional BFTs, we didn't really hear about blockchain, right? The consensus mechanisms themselves can, of course, be used for the blockchain because you can just extend it by the chaining of the individual blocks. You can be agreeing on them. But the part that didn't really allow such large scale is basically the information. And the drawback is that you actually have to know the individual peers and you have to communicate with each of them, which of course doesn't really scale, right? If I have to send everyone a message and each of the individual parties have to communicate among each other, maybe you can have 10, 100, but if you want to have thousands or even millions of nodes in the system, it's becoming really problematic, right? So for that, the main disadvantage of these deployments was the scalability in the number of nodes. And with that basically came the solution offered by Satoshi Nakamoto with Bitcoin that actually look at the problem from slightly different perspective and rather was like, do I actually need that all of the peers in the systems are communicating? They rather decided to focus on the aspect on who actually will be the only single proposer in the system, and they a little bit try to actually slow down the protocol by that. But overall, they actually were able to achieve the scalability. When we talk about Bitcoin or in general blockchains, we usually talk about deployments on hundreds of thousands of nodes. And for that basically was the main innovation of Bitcoin, where in the previous state-of-the-art solutions, usually you had a leader that was talking to all of the peers. They had to agree and propagate a lot of messages, right? Which is of course not very scalable. On the other side, in Bitcoin, you have to solve this proof of work puzzle. What does it mean? You are like mining locally on your machine, you try to solve certain hash basically and identify the right ticket to the lottery. And once you find it, you actually are selected as a block proposer and you can propose a block and propagate it to everyone. And that's it. Basically, you don't have to really communicate with all of the other parts about the information that you have. You don't have to really talk about the transaction that you have about the local view. You are just basically trying to solve the puzzle, and once you solve it, you are allowed to propagate, which is a very neat solution, but comes with certain strings attached, of course, always. And in this context, the strings attached are basically once you propose the block, how do you actually ensure that you are the only peer in the system? that actually is propagating the block and not other parties, right? Because since you have a distributed system of hundreds of thousands of nodes, each of you are actually hashing, right? They're actually trying to solve the puzzle, and there could be multiple winners. And of course, this results in something that we will call soft forking, in case basically there are multiple proposers within the given round, and later on you still have to kind of gain the confidence that the block that you have proposed and the block that is building on top of that are actually the correct information that we are willing to work with. So this is something to keep in mind when it comes to the comparison between the traditional BFTs and the innovation coming with Bitcoin. Looking into the second generation, we are talking about Ethereum. That was introduced by Vitalik Buterin in 2015, where the main innovation, of course, in addition to the scalability aspect that was introduced by Bitcoin, we have to keep in mind two additional aspects, which is the blockchain computer. As you know, Ethereum main breakthrough basically was by introducing smart contracts that allow you for computing on blockchains. Basically, you can have programmability. For the mind, we are also talking about quasi-Turing complete language, which means that you have many capabilities, as you know, from other programming languages. The only part you are here constrained by the duration and by the cost of your smart contract execution. And second part, building on top of that, is composability. That basically allows you that if you deploy multiple programs on the blockchain itself, they can actually also interact with each other and can talk to each other, which is very great. And for that, sometimes we are talking about smart contract platforms or basically internet computer, where you can actually deploy any type of logic on the chain that can handle such type of processing. And for application, we of course see a lot of interesting aspects when it comes to complex calculation, exchanges, DeFi, right, and so on and so forth, which I think will be part of the motivational talk afterwards by Professor Welbe, that will be covering into the various combinations of the usability and what you can build on top of blockchains as well. So we solved it, right? We basically have programmability, we have the scalability, so why do we even worry about the third generation? Everything is there, right? Unfortunately not, because when it comes to scalability, it's again a bit of spectrum. We are talking, for example, about the scalability in the number of nodes. But second aspect, we have to take into consideration actually how many transactions the system can handle per second, right? Because if we want to have mass adoption, this is something I'll be talking about later on, we want to make sure that thousands of people can actually interact with the system for not too high cost and ensure that the system actually scales also with the number of users and number of interactions with the system. And this is basically why we have the third generation of blockchains, which in general try to solve so-called blockchain dilemma. That was also a term coined by Vitalik Buterin, where we have security, we have decentralization, and we have scalability. And the claim is that at no point in time, more than 2 out of these 3 properties can be ensured. Meaning that you're going to have a blockchain that is secure, scalable, and decentralized. And basically here you can see it's opening a broad area of design space where you can try to design your own blockchains that tries to solve either the decentralization and scalability, because usually you don't want to sacrifice that much of the security, right? At the end, you have quite a high amount of money locked in such systems, and it basically allows for a lot of design decisions that you can do, like do you want to have many nodes, less number of nodes, do you maybe have certain semi-trusted peers in the system that have more power than others, and so on and so forth. And for that, we can see a lot of innovation and a lot of activities on the consensus level of blockchains that basically aim to solve the blockchain dilemma. But also, as mentioned before, we also start to see a slightly different shift, not that we assume that will be one blockchain that will do everything, but actually we start to see more custom main blockchains that are meant for specific use cases and specific purposes. So this is also quite an interesting shift when it comes to designing such deployments. There is, of course, as I was mentioning, a lot of aspects we can think about from the design perspective. So I already briefly touched upon the security, scalability, decentralization. But as you can see, it's not only one metric one has to consider for that, right? There is, again, a large spectrum. Someone talks about security. Do we talk about security against what? Do we talk about security against malicious parties? Do we talk about security when it comes to the network behavior? If there is too much delay, how does the system handle the delay? Are we talking about non-responsiveness, that let's say a party that we are sending the message to doesn't receive it? Or do we actually talk about malicious parties in the system that actually are actively trying to break the system? So again, a lot of stuff one has to keep in mind. For scalability, in general, we are talking about one metric is the transactions per second, TPS, right? But in general, I think we should focus on the number of interactions with the system we can have, like for not only writing to the chain, but also reading from the chain. Number of addresses, meaning actually how many users can the system handle. And I think third part is the number of nodes, meaning actually how many parties can run and participate in the consensus until it becomes not really scalable and performant. For decentralization, I think there is a lot of discussion regarding staking, mining, right? Like how much power each of the individual peer in the system has. It's definitely, again, a lot of stuff to consider. But of course, I think this is the very cool part about blockchains. It's not only about the technical parts, but it's also about the combination of interdisciplinary teams, because, for example, governance is also a very decisive factor when it comes to operating a blockchain, because at the end, the technology should enable it. But at the end, there have to be people that are using it, that they are deciding about the aspects on what will be the next step for the protocol itself. And sometimes in this context, we're talking about so-called social consensus that basically runs on top of any type of blockchain out there, and it's very important to keep this in mind. Next part is the node participation. That is something I will be talking about on the next slide. Peer-to-peer network, and of course many other parameters such as finality, block size, throughput, forking. I briefly touched on that when it comes to, for example, Bitcoin. And of course, I think very important for developers such as you that are here and want to learn about technology, maybe want to deploy their own smart contract, which will be part of the Blockchain 101 track. That will be definitely something interesting for you to have a look at on how to do it, but also understand actually what are the capabilities of the smart contracts and what do we have to keep in mind when it comes to such deployments. So continuing with the next slide, that basically is focusing on the node participation. First, the disclaimer, proof of work and proof of stake are not consensus mechanisms. Sometimes it's being used interchangeably inside of the literature. Just please try to forget that this is the case, because it's not. Proof of stake and proof of work are Sybil resistance mechanisms, meaning that you can also think of it in a more lightweight fashion, that basically if I don't have any power, meaning I don't have any hashing power, or I cannot prove any work, right, or I don't have any stake, I cannot actually even go and participate in the consensus. So basically the weights, you can think of it like a gatekeeping on actually who can participate in the consensus. So for example, for Bitcoin, right, the consensus mechanism is called Nakamoto consensus, right? But it's not called proof of work. So proof of work is just a mean on how to actually differentiate it, who can actually participate in the consensus itself. As you can see, there is again a variety of options, especially for the proof of stake, that is kind of trying to solve the energy inefficiency coming together from the proof of work, right? Because you're solving puzzle that many times, depending on the solution out there, actually do not really contribute to anything particular. So the proof of stake is try to go more the aspect like, in understanding the direction of, depending on how much stake I have, the higher the power I have when it comes to voting. And let's say there are different also flavors of that. So you can, let's say, delegate your stake to someone who will be voting on your behalf, maybe in a more centralized fashion, right? This is something that, again, comes the design decisions. What does it mean if I have someone who's voting on my behalf? Is a person then trusted, or the entity trusted, or not? You know, can they abuse it? How? And you can see a lot of questions actually you can already ask from this type of perspective. Second approach is bonded proof of stake. So usually, let's say you lock your stake. You can think of it like a saving account. You lock your stake in the saving account, and your account is basically working for you, right? It's participating in the consensus, and you, let's say, lock it for a year, and after a year, you can take your rewards and your stake back. So again, different approaches, right? And if you misbehave also during the locking, you can actually also be slashed, because actually the stake itself is being locked and you don't really have any access to it. And the last flavor is pure proof of stake. This would be, I guess, the one that we would be striving for, right? Because it means that basically anyone who has a certain stake can actually participate and vote in the system. However, here again, it comes a bit more responsibility for the users in such a system, right? Because if everyone can vote, it's basically permanent referendum about what decisions are we going to make, and we have to also ensure that the users in the system actually are able to protect their system, because at the end, if they get compromised, it's something that either they can lose the stake, not maybe as easily, but rather it's important that the malicious parties out there do not hold more than a certain portion of the stake and can later on change the direction of the chain. I briefly touched on that, but I think this is just a slide to provide the final overview of the types of consensus mechanisms, and when it comes to the other parameters regarding forking and finality. In general, we basically see two main families of blockchain consensus mechanisms out there. That is like the chain-based approach, which basically is the type of Bitcoin, right? That we basically are broadcasting our block, we are building on top of our block, and we are gaining more confidence into the block that actually were proposed. Or we have the traditional, or close to the traditional BFT-based approaches, where we deploy a single block. Later on, we basically agree on it, and we ensure an instant finality, which I think is, again, quite interesting. However, depending on the solution, there might be limited in scalability. And when we also look at it from the perspective of what are actually the differences between the Bitcoin and Ethereum's and other type of blockchain type of consensus mechanisms and the traditional BFT mechanisms, in general, the difference is focus on the part that I was mentioning at the beginning, that we have either a fixed number of participants, or for blockchain, especially permissionless blockchains, we actually can have parties that are coming and leaving, perfect timing, and they can basically later on join maybe on a corresponding round in the system, or even later on during the system itself. So I think it's very interesting to see the differences, because once you can a little bit change the focus, you can actually see that a lot of different type of security guarantees have to be proven and understood, and at the end we are still actually able to achieve very, very interesting results, where the main idea, we are selecting committee leaders, proposals, and so on in the system still stay the same, but the way on how do we select such parties is very different, and in general it starts to go in the direction of game theory and probabilistic type of behavior that we see in the blockchains that allow the scale, but again, maybe come with a certain other strings attached. So overall, as outlined, the main innovation of Bitcoin was to achieve the scalable BFT solution by basically aiming towards the probabilistic nature of the system. And at the end, also like the current academic approaches basically see that maybe actually thinking about it from the perspective of probabilistic is good, and actually it's something that people start to see as a state of the art when it comes to certain type of deployments as well. And the last part of the talk, right, now we're gonna cover it, okay, there's so many solutions out there, so many design space, what can we do? And now comes the part like of the mass adoption, right? So I think from the technological perspective, we have to ask ourselves several questions or identify suitable steps. So the first one is, what do we take or think of what is mass adoption, right? So for me, in general, what I would consider as mass adoption, I would think of having thousands of distributed applications that are able to do thousands of transactions per second, right? Because you want to have a lot of people on board that are interacting and they are generating a lot of float, which of course, if you do roughly the math, you actually end up with having millions of transactions per second the system can handle. So if we try to decompose it into the individual steps, firstly talking about, can we actually deploy thousands of smart contracts and applications on the chains? Definitely. Most of the chains out there can actually handle such large amount scale of deployments, because at the end you deploy your smart contract once and you are later on interacting with it without any big issues. So it's not a big deal. However, with the second step, if there will be thousands of interaction with each distributed application, becomes a bit tricky, right? Because at the end, there are some solutions out there with certain constraints out there, but I think it will be actually interesting how we're gonna innovate in this direction, because I think still we are a little bit, it's a work in progress, let's put it like this. But looking back on where we were in 2009 and where we are now, I'm quite confident that in the next years, we can actually reach such type of technology ripeness for literally large scale mass adoption. And of course, the third step, which is I think something that we'll be discussing, and it's great to see so many people in the audience, is to bring actually users on board, right, that actually want to interact with the system. So overall, I think interesting times ahead, a lot of research, development, new applications to be built and then developed and bring new users that will be blockchain native into the space. And of course, there is always space for early adopters like yourself that are part of this cool conference. So thank you very much. I hope you enjoyed the talk. You roughly now have an understanding of how the blockchain itself evolved over the years. And in case you are interested, feel free to reach out on Twitter or LinkedIn. And you can also have a look at our chair website. Thank you very much.
Thank you so much, Filip.